Hi, here we are discussing about a project low power and high speed SRAM cells with a double node upset self recovery for reliable applications. Here the SRAM is used in many critical applications such as aerospace, defense and medical electronics because it offers a fast operations and low power use. However, as CMOS technology scaled down to smaller size, SRAMs becomes more sensitive to radiations. So this creates a problems because the charged particles can cause a single node or double node upset that flipped to store data. So the existing hardened SRAM cells like RHD12 to RHM, it helps to improve reliability, but they still suffers from the drawbacks such as a higher delay and more power usages and limited ability to recover from double node upset due to large area. To understand these issues to better, all these cells are designed and evaluated in 22 nanometer CMOS technology and compared in terms of delay, power and area based on the gaps which observes two new SRAM cells called S6P8N and S8P6N are developed. So this designs uses to improve the transistors arrangement to recover fully from all single node upset and from most double node upset. This S6P8 cell focus on lowering average voltage, while the S8P6N cells aims to improve the read and write speed. Okay, the main novelty of this work is that the proposed cells achieves a balanced improvement in reliability, speed and power without increasing the circuit complexity. All designs are created and tested using a ternary DA with a 22 nanometer CMOS module. The performance is analyzed through power, delay, area with a read and write access time, static noise margins and Monte Carlo simulations. The result shows that the proposed S6P8N and S8P6N cells offer a strong practical solution for future radiation tolerant memory systems. Now we can verify the paper. So this paper is fully designed for the double node upset self recovery SRAM cells. Okay, so here we have totally designs 14 number of SRAMs in this work. Okay, so here the first designs it will become with RHD12 and QCCM12T and QUCCE12T and RHMD10T and SCA14T and RHM12T, S4P8N, S8P4N, RH14T, HRLP16T and CC18T and RHM. Okay, so these are the existing method of the architectures. It will be take more number of transistors and it will be come with a drawback stages of more delay and power consumptions. Okay, for this designs it will be reduced the number of transistors and the novelty architectures it will be created in the figure 2 architecture. So it will be present with the S6 and P8N structure. One it will be come with the 18T transistors due to lowering average power and the voltage stability with a dual node upset configurations. Okay, and the same method it will be used in the proposed another one model. So here it will be designed with the S8P6N architecture. Here this architecture S8P6N it will be present with 18 number of transistors and this S6P8N also present with 18 number of transistors. Okay, so but it will be come with very less power consumptions. Okay, but the radiation hardened of the 10T transistors in the existing model it will be come with a very less number of transistors count, but it will become with a more power consumptions and delay consumptions as per the comparisons rule. Okay, here we have done this figure 2 architectures and as well as the figure 7 architecture design as a proposed method, and the existing architectures also developed in 22 nanometer CMOS technology and they proved the performance in ternary DA work. Okay, so now we can verify the output. So here the first architecture it will be present with RHD12. Okay, so here this one RHD12. So this is the core of the architectures. So it will be present with the basic SRAM architectures. So this is a one type of inverter and this is another inverter and this is a write signals. Okay, so bit line and bit line enable and this is a write line. Okay, so whenever the write lines it will be active at the time whatever the bit line and bit line BLB, okay, the complement of the bit line. Okay, the data it will be written into the SRAMs, okay, and we will get a output in Q and Q bar. Okay, so this is the features of basic SRAM architectures. For power improvement, it will come with the additional 2 PMOS transistors. Okay, so here we'll run this work. Okay, we'll get the result. Okay, so here you can verify the BL and BLN. Okay, so at the time of WL. Okay, so this is a write operation. Okay, so once you are writing the data here, the WL it will be available. At the time we are writing the data BL into the Q. Okay, so here we are writing the data Q equal to 0. Okay, and here we are writing the data Q equal to 1. Okay, at the time of WL it will be writing the data, and balance time it will be maintaining the data. Okay, so this is a proper functionality of the SRAM architecture. Okay, the same part of the SRAM functionality we have proved in all the 14 number of SRAM architectures. Okay, and the proposed architectures it will be present with the S6P8N architecture. So this one. Okay, so we'll execute this. Okay, so this is a proposed architecture S6P8N, and another one is S8P6N. So this one. Okay, so here all the architectures it will be done with 0.8 input voltages. Okay. Okay, and the power consumptions and delay count and the transistors count it will be analyzed in the T-Spice. Okay, so here this is a T-Spice architectures. Okay, here you can analyze it out file. Okay, so this is a design of S8P6N architecture. So MOSFET equal to 18, and power consumptions it will be present with here. So 9.1629 e power minus 7, and delay it will be take for 1.841 e power minus 7. Okay, so this features updated in the comparisons table. Here the comparisons, CMOS technology is 22 nanometer, input voltage is 0.8 input volt, and we have designed all the 14 number SRAM architectures. Okay, and finally we have written an abstract document for this project. So title, base paper abstract, improvement and proposed title, proposed abstract, existing disadvantages, proposed architectures, and proposed architecture description, proposed systems, related notes. Okay, and finally we come up with the literature review and references. Okay, thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research. Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.